So the Center for Disease Control and Prevention reported that 20.9% of American adults smoked regularly. Again, every question may not ask you to do this, but it's a good idea to go ahead and talk about your sampling distribution when you realize you're working with one. And this says, what would the sampling distribution look like? Well, I would start off and I would say that P, whatever um, the true proportion would be, that would be the mean of the P hats. And it's this idea that we had before. Remember before we said, IQ scores are distributed normally with a mean of 100. Well, we're saying that the mean of all people's IQ would be 100. That's a mu idea. And that the mean of any X bar that we took would be that same number. Same thing here. We're saying that we know, or this is being reported, we're treating this fact, that in this year, 2004, that 20.9% of American adults smoked. We're treating that as the truth, and we say that that would be the value of P, which is the mean of all the P hats. So we have our center. It's just given to us right there in the problem. Then we need to find the standard deviation. That's where that formula is going to come in. That's that square root PQ over N. And then we would need to say, do we have the conditions met for this to all work and have our normality? We would check if X is binomial, to work through those checklists. Do we have a fixed number of trials? Yes, we have 100 American adults. Would the probability stay the same? Yes, we would say that if we're randomly sampling 100 people, the probability that we pick one and they smoke would be the same. It wouldn't, we're not biasing our sample anyway. We're not like we picked our first 50 by going to a, smoky bar, and then we picked our next 50 by going to, I don't know, some place where people don't smoke, right? we're not doing anything wonky like that. There's nothing in the problem, so we're not going to make anything up there. So we just say, yeah, we're just randomly picking people, so the probability any of them smoke stays constant. That's our second thing. We only have two options: you're either a smoker or not, and you can't be both at the same time, so that makes them mutually exclusive. And the trials are independent, meaning that we're not picking a person, asking them if they smoke, and then the next person, doesn't overhear it and say, "Oh yeah, they smoke. I smoke too," right? We would say they're independent. That people are going to answer whatever they're going to answer, and the answer for the first person does not affect what happens to the next person. So I can check through, make sure that we have a binomial distribution. It seems good. And then we multiply n times p and n times q. Again, we already said p is that 20.9%. Multiply that by 100. Q is 1 minus that. Multiply that by 100. And we can validate that we have both of those at least 5. So we would say p hat is approximately normal because all three of those criteria were true. Here would be our mean. Here would be our standard deviation. I'm going to rewrite this with the number just so you can make sure you can calculate that. Notice we took our percent. We convert to decimal. We're always going to convert to decimal if it's not given to you that way to start. We never work with percentages. We can write a number that way. It's nice and pretty, but we're never going to work with the percentages. We're always going to work in decimal form. When we do that math out, we get the answer for that standard deviation would be 0.04. And I'm going to justify why I said that by writing out what we talked about here with our three assumptions that we're checking. X, the number of American adults in the sample who smoke, is binomial. N times P is at least 5, and N times Q is at least 5. Next, we're going to calculate the probability that the sample proportion who smoke will exceed 0.25. So I'm asked to find the probability. So I'm going to first write a probability statement. Notice before we had probability statements, we had probability of X, we had probability of Z, we had probability of X bar. Now we're going to write the appropriate statistic. It says calculate the probability that the sample proportion who smokes. So I need to write the probability of P hat. Just make sure you're writing the appropriate symbol. And it's just like before. We're going to keep our symbols on the left, keep our numbers on the right. We're going to standardize both. We're going to subtract the mean and the standard deviation. Now, there's no mu symbol, there's no sigma symbol, but that's okay because we know what the mean is. The mean of all the p hats is p, and the standard deviation is square root pq over n. We've already found those numbers in the step before. And so it would look like this. Subtract p, that's what p is, divide by the standard deviation, that's what it is right here. We actually know the number is 0.04. We know because we've standardized and because we said that this was normal. Remember, this was standardization piece plus this was normal. Let us use a Z. We just got to work through the math now. We have a greater than probability question. So because it's a normal setup, we want to work that into a less than. So we work with complement, go to the table, and we can get our answer. And then the last example for this problem says same setup, but what if we had a sample size of 400 now? And it's the same thing. This would be a good opportunity for you to pause and work through this. It should be fairly simple for you because it's the same setup. The mean is going to be the same. It's just now we're going to have to change one aspect of this problem. Everything else is going to work through the exact same though until we get our answer. And for our last example here, again, good opportunity now that you've seen one, maybe pause, see if you can work through. If not, see how much you could do kind of on your own or see if you can get it right, come back and check, whatever it may be. If we have an airline that knows that 95% of people with tickets will show up for their flight, as we had in the previous problem, we're going to assume that that is P, our true probability of success. And we're interested in this question of what's the probability that at least 90% show up if we have 150 people who bought tickets for this flight. And so again, write out your probability statement. You need to make sure we understand why this is 0.9 instead of 0.95. And this is the difference between understanding a sample proportion from a population proportion. And this is the case that which one is my assumed known truth and which one is the sample proportion that I'm interested in my probability statement. Notice my probability statements find the probability that at least what, 90%. That's why that goes there. Also notice of the 150 people of a sample. So this goes with the sample proportion because this is what I'm talking about. This is my known truth that I've established as fact that 95% of people show up. From there, just like before, standardize. How did I get that number? I plugged in 0.95 times 0.05 divided by 150. That's where you get this number from. And continue just to work through the problem like we've been doing. This last part here, it should be pretty downhill once you get there because we've been doing lots of problems like that. We could also work an in-between question, find the probability between 90 and 95% of the people show up. It's going to be, again, key thing, finding how to write a probability statement. But we had in between those two values. Just like before, we're going to standardize left, middle, and right. Middle will keep symbols with symbols. Other side will go numbers with numbers. Notice that right side's going to be 0, no matter what the denominator is, because we picked the same value as the mean of the p-hats for that bound. And then rewrite that as probability z less than 0 minus probability z less than negative 2.81. Same trick we used before. Go to the table for both to get our answer. Now, this last one's a little bit interesting. The plane only holds 145 people. Find the probability that someone shows up for a flight but cannot board. Now, this is where the fact that x is binomial, i.e. a subset of discrete. So x is discrete, there's gaps. But p hat, which is what we're working with in our probability statements, is continuous. It's going to cause a little bit of a kink because there's two ways you can work this problem and both of them would be perfectly acceptable. You can view this as what is the probability that more than 145 people show up, so it'd be greater than 145, or what's the probability that the 146th person shows up, so it'd be greater than or equal to 146. If we just stick to x being binomial, those are equivalent statements because greater than 145 means everybody that's 146 and up. That's the same thing as saying greater than or equal to 146. But because we have to divide by n and convert these to p hat, which is continuous, now there's decimals in between that we are not considering. So you could work this either way. It's a little bit wonky, the fact that you can work it both ways, but both of them would be acceptable, even though you're going to get drastically different answers. So hopefully if you paused and worked ahead, you got one of these two. The first way is to say, what if we got more than 145 people? That'd be p hat greater than 145 over 150. Convert that to decimal, and you get that 0.9667 and work the problem. Greater than, so we're going to work with complement just like always. If it had been less than to start with, we wouldn't have to do that. Or we can work with this greater than or equal to 146 idea. But notice that's going to be a different decimal. And remember, in continuous, the or equal to doesn't matter. So the fact that we didn't include the equal to here, but did include it here, doesn't actually affect our calculations because p hat is continuous, even though we know that we started off by writing out two different statements because we started off with actually discrete data. Again, kind of wonky, but notice by giving you a different decimal here, it'll give you a different z-score to look up in the table or in Excel and lead you to a drastically different probability. And then to close up, check and adjust all of our assumptions. N times P and N times Q are pretty straightforward checks. Both of them are at least 5. One of them is kind of close. Both are at least 5. And then we have to say, is X binomial? There are only two options that are mutually exclusive. You either show up for the flight or you don't, and you can't do both at the same time. We have a fixed number of trials, there's 150 tickets bought, but are the trials independent? Does the probability of one person showing up affect the next? And if all of the tickets purchased are purchased by individual people who are not related or know anybody else, you could argue that they are. However, we know that people don't often travel alone. Sometimes they do, but oftentimes people travel in families or in groups of people with friends. And if one person misses the flight, it's likely the other people were in the car with them and also missed the flight, or it's likely that they traveled in the subway with them, or it's likely that they decided not to take the trip because one of the people got really sick and the other person didn't want to go by themselves, right? Imagine going on a trip with your significant other and that person being sick as a dog. You're not going to go off to Hawaii by yourself, probably. Hopefully you'd stay back and take care of, of your girlfriend, boyfriend, whatever. And so we would say that X being binomial is debatable at best, because I would say that the trials are probably not independent. And I ran out of room on the slide, but we want to make sure we summarize this together and say, how do we feel about our results? And I would say that our numbers might be off a little bit because we made an assumption that X is binomial in working the problem. That's why we went through that painstaking work early on at the start of this lecture about what is the mean of the p-hats and what is the standard deviation of the p-hats. It kept coming back to we have to assume X is binomial. That's why those formulas work. If X isn't binomial, those formulas for the mean and the standard deviation don't necessarily work. And so that means my math might be off a little bit. I might have said the probability was 17% or 10% or 50%, and it might not be. It might be a little bit higher, a little bit lower. And that's the issue with failed assumptions is it might have caused us problems, it might not have caused us problems, and even if it did cause us problems, we don't necessarily know how big those problems would have been. And so we need to make sure we kind of summarize that. Again, I ran out of room on the slide, but that's what we want to summarize it in some way, shape, or form that we checked our assumptions, but we probably have a little bit of an issue because one of our key principles that we needed to have as an assumption that X was binomial is likely not true. And then I put on the next page for you just a little summary, little picture for you here of what we're doing. Again, remember, we're not going to actually go out and get a bunch of p-hats. We're not going to go out and get a bunch of x-bars, but it's this idea of I need to know theoretically what would they look like so that when I take my one p-hat or my one x-bar, I know what to compare it to. And so this is kind of an illustration for you to see what that might look like. And then a table here for us to keep things straight. Notice that left side is a proportion problem. The right side is a mean problem. What's the shape, center, and spread? When is n large enough? Notice on the proportion part, there is no talk about X being binomial. That's because remember that X being binomial is what lets us do this right here for center and spread. It doesn't actually matter about is n large. N is large only matters about n times P, n times Q. Okay, but we need to check if X is binomial because that tells us this is accurate. Okay, so we have to check, is X binomial to see if that worked? We have to check, is N and P large enough to see if we have that approximate normality in order for this z-score to actually correctly lead us to our z-table or to the appropriate function in Excel. And then for mean problems, just as a reminder again, we check first if X is normal. If so, then X bar is exactly normal. If that doesn't work, then we check to see is N large enough. Do we have any greater than or equal to 30 and or checking that skewness, large, we need an way bigger than 30. If it's not, we can do an n less than 30, and that gets us to this approximate normality. So just a little table here to remind us, little kind of place to turn to quickly as you're trying to make sure you've sorted through all of this in your head.